This is a short tutorial on how to model a thirsty duck TDP series floating outlet and skimmer in WWHM2012. This tutorial also includes a procedure for optimizing the volume of detention storage. For this tutorial, we will assume a pre-development scenario with the following hydrologic characteristics. The project is located in King County. The nearest rain gauge is CTEC and the precipitation factor is 1.000. The basin area is 7.84 acres of moderately sloped forest in C-type soils. The basin is connected to the point of compliance by surface flow and interflow. The post-development or mitigated scenario for this tutorial has the following hydrologic characteristics. A pervious area of 2.36 acres of moderately sloped lawn in C-type soils. Impervious areas consisting of 1.53 acres of moderately sloped road, 2.69 acres of flat rooftops, 0.65 acres of moderately sloped driveways, and 0.37 acres of moderately sloped sidewalks. For purposes of comparison, we will start with a vault and riser design, which WWHM2012 indicates has passed. In this example, we will use the following data: a length of 131 feet and a width of 145 feet, an inside height of 8 feet, and the live storage starts at elevation 0.00. The assumed outlet riser has the following features. The first and lowest orifice has a diameter of 1.53 inches and an invert elevation of 0.00. The second orifice has a diameter of 2.52 inches and an invert elevation of 4.67. The third orifice has a diameter of 1.53 inches and an invert elevation of 5.25. The top elevation of the riser is 7.00 and the riser diameter is 18 inches. For this pre-development scenario, the WWHM2012 has calculated the 2-year flow to be 0.2334 CFS. The Washington Department of Ecology Flow Control Standard limits the number of exceedances between 50% Q2 and Q2 to no more than 100% of the pre-development exceedances. Since the WWHM2012 considers flows equal to 50% of Q2 to be an exceedance, we will start by designing the thirsty duck for 48% of Q2, 0.112 CFS. Using the orifice diameter selection chart in the TDP series design spreadsheet, find the orifice diameter corresponding to 48% Q2. For this example, an orifice diameter of 2 inches corresponds to a flow rate 0.112 CFS. Note: green bars are thirsty duck model TDP184, while blue bars are thirsty duck model TDP248. Create the thirsty duck rating curve by first opening the Data Entry tab in the TDP series design spreadsheet. Enter the thirsty duck model number. For this example, use model TDP184. Then enter the nominal orifice diameter. For this example, 2 inches. Next, enter the design elevations for the project. For this example, the maximum storage elevation is 8.00. The minimum discharge elevation is 0.00, while the design peak stage is elevation 7.00. We will not assume there is any tailwater influence in this example, therefore enter the tailwater elevation at 0.00. Next, input a trial operating head value and vary the value until the design flow rate equals the target flow rate. In this example, an operating head of 10.75 inches yields the target flow rate of 0.112 CFS. Note: the goal-seek function in Excel can be very useful for quickly finding the required operating head. Thirsty Duck recommends rounding the operating head to the nearest quarter inch. Since Thirsty Duck is controlling the system water level, this is a Case A installation. If you are not familiar with the difference between Case A and Case B installations, please see our short tutorial on the hydraulic principles behind the TDP series floating outlet and skimmer. Finally, enter the rating curve computation increment. The increment should be set at 1/100th of the total depth of storage, 0.08 foot for this example. Open the Stage versus Area tab in the TDP Design spreadsheet. Enter the length and width of the storage. For this example, the length is 131 feet, the width is 145 feet, and the side slope is 0, since the vault has vertical walls. Open the Stage versus Discharge tab in the TDP Design spreadsheet and enter the data for each of the orifices on the outlet riser. Do not include the lowest orifice from the comparison vault design. Thirsty Duck will have a discharge elevation of 0.00 and will replace the lowest orifice. For this example, enter the orifice data as follows: Orifice 1, active, no. Orifice 2, active, yes. Invert elevation 4.67 feet, diameter 2.52 inches. Orifice 3, active, yes. Invert elevation 5.25 feet, diameter 1.53 inches. Notch, active, no. Rim, invert elevation 7.00 feet, diameter 18 inches. From the Basic Elements menu in WWHM2012, create an SSD table. Connect the basin to the SSD table and connect the SSD table to the POC. Change the header on the fourth column in the SSD table from Not Used to Manual. From the SSD Table tab in the TDP Design spreadsheet, select the stage, area, volume and discharge data. Right-click and select Copy. Paste the data into the SSD table in WWHM2012 and finally run the scenario. Open the Analysis window in WWHM2012 and select the POC1 tab. Verify the facility has not failed at the lowest regulated flow rate, 50% Q2. For this example, the facility has passed. If the facility does not pass, reduce the design flow rate for the Thirsty Duck until it passes. Note the mitigated exceedance curve is clearly separated from the pre-developed exceedance curve, which indicates a reduction in volume may be accomplished. The greater the separation between the curves, the greater the potential volume savings. Start the storage volume optimization process by selecting the Stage versus Area tab in the TDP Design spreadsheet. As a rule of thumb, start with a 20% reduction in either the length or width. For this example, we will reduce the width from 145 feet to 116 feet, a 20% reduction. Now, select the SSD Table tab and copy the new data into the SSD table in WWHM2012. Then, rerun the scenario. Open the Analysis window in WWHM2012 and click on the POC1 tab to review the results. For this example, WWHM2012 indicates the reduced facility has passed. Note the exceedance curves are still clearly separated, which indicates a further but smaller reduction in volume may still be accomplished. For this example, we will attempt to reduce the width by an additional 4 feet. Rerunning the scenario with a width of 112 feet yields a failing condition. However, the failing condition occurs in a localized area at the upper range of the exceedance curve. This indicates a passing condition may be achieved by optimizing the design of the riser. Before adjusting the diameter or elevation of an orifice, it is helpful to understand the effect each change has on the exceedance curve. Note the mitigated exceedance curve has 3 distinct arcs. Each arc represents a flow control mechanism on the riser. For purposes of illustrating the effect an adjustment to an orifice has on the exceedance curve, we will manipulate the upper orifice. Increasing the diameter has the effect of rotating the arc to the right, while decreasing its degree of curvature. Decreasing the diameter has the effect of rotating the arc to the left, while increasing its degree of curvature. Increasing the elevation has the effect of rotating the arc to the left while raising the beginning point of the arc. Decreasing the elevation has the effect of rotating the arc to the right while lowering the beginning point of the arc. In general, the riser should be optimized in the ranges where the pre-developed and mitigated exceedance curves have the greatest separation. After several iterations, the following configuration yielded a passing solution with a total reduction of 34,584 cubic feet of vault storage. Vault dimensions 131 feet long by 112 feet wide, with an inside height of 8 feet and live storage starting at elevation 0.00. The outlet riser configuration, Thirsty Duck model TDP184 at elevation 0.00 with a 2-inch diameter orifice operating at 10.75 inches of head. Orifice 1, diameter 2.25 inches, invert elevation 3.55. Orifice 2, diameter 1.75 inches, invert elevation 4.80. Orifice 3, diameter 1.00 inches, invert elevation 5.50. Top of riser, elevation 7.00. Thank you for watching this short tutorial on how to model the Thirsty Duck TDP series in WWHM 2012. If you have any questions or comments regarding this tutorial, please feel free to contact us through our website at www.thirsty-duck.com. We are always happy to review or assist with modelling at no charge.